Welcome back, everyone. It is great to have you here for Chapter 2 of Droneverse, Understanding Drones Worldwide. Before we dive into today's session, let's take just a moment to recap what we covered in Chapter 1, because everything we do today builds directly on that foundation. In Chapter 1, we started right at the beginning. We answered the most fundamental question of all. What exactly is a drone? We explored why drones exist in the first place, tracing their origins from military prototypes to the consumer products sitting on store shelves today. We looked at where drones are being used, from farms in Punjab to film sets in Hollywood, from disaster relief zones in Turkey to package delivery trials in Singapore. We then went into how drones actually fly. We talked about aerodynamics, lift, thrust, drag, and weight, and how a drone balances all four forces just to stay in the air. We explored the different categories of drones. Consumer drones that anyone can fly straight out of the box, FPV drones that give you that first-person racing experience, agricultural drones that spray crops across hundreds of acres in a single day, industrial drones built for inspection and heavy lifting, and military drones that have genuinely changed the nature of modern warfare. We also covered drone regulations, because flying is not just about skill, it is about law. We discussed the DGCA in India, the FAA in the United States, ESA in Europe, and several other global aviation authorities that govern the airspace we fly in. That was Chapter 1, a broad, exciting overview. Now, in Chapter 2, we are going to do something different. We are going to open the drone. Literally, we are going to look inside and understand what is actually in there, what makes it tick, what makes it fly, what makes it know where it is. By the end of the session, you will not just see a drone as a flying object. You will see it as a system, a collection of carefully engineered subsystems working together with extraordinary precision. Let us begin. Here is something I want you to remember. No matter what drone you are looking at, whether it is a tiny 5-inch FPV racer, a massive agricultural sprayer with a 20-liter tank, or a military surveillance drone flying at 30,000 feet, every single one of them has the same 7 fundamental subsystems. 7. That is it. The frame, the motors, the ESCs, the flight controller, the battery, the propellers, and the radio system. These are the building blocks of every drone that has ever flown. Let me walk you through each one, what it is, what it does, and what happens if it fails. Think of a drone like the human body. That analogy will help you understand the relationships between these parts in a way that no textbook diagram ever could. The frame is the skeleton. It is the structural backbone that holds everything else in place. Just like your skeleton gives your body shape and holds your organs in position, the frame gives the drone its geometry, its rigidity, and its mounting points. The motors are the muscles. They are what create movement. Your muscles receive signals from your nervous system and contract to create motion. The motors receive electrical signals and spin to generate thrust. The ESCs, the electronic speed controllers, are like the nerves that connect the brain to the muscles. They carry the signals and translate them into actual physical action. The flight controller is the brain. It is the central processor, the thing that thinks, decides, and issues commands. Everything flows through the flight controller. The battery is the heart. It pumps energy through the entire system. Without it, nothing runs. The propellers are the hands and feet, the end effectors, the things that actually interact with the physical world. They take the rotational energy from the motors and convert it into the force that lifts the drone off the ground. And the radio system, that is the sensory link between you and the drone. It is how the pilot's commands travel from the transmitter in your hands to the receiver on the drone. Think of it as the communication channel between a commander and the field team. Now let us go deeper into each one. Starting with the frame. The frame is the first thing you notice when you look at a drone with its shell removed. It is a collection of arms, a central hub, and sometimes a body plate, all engineered to be simultaneously light, strong, and rigid. Why does that matter? Think about what a drone's frame goes through. It vibrates at thousands of revolutions per minute from the motors. It impacts the ground, sometimes hard. It flexes under load. It twists in the wind. The frame has to absorb all of that without cracking, bending, or transmitting vibration up to the sensitive electronics mounted inside it. So what materials do engineers use? The most common is carbon fiber. You have probably heard that term before. It is used in Formula 1 cars, aerospace, high-end bicycles. Carbon fiber is an extraordinarily interesting material. It is made from strands of carbon atoms, bonded in a crystal structure, woven together and set in resin. The result is a material that is lighter than aluminium, but stronger than steel in certain loading conditions. For drones, carbon fiber has three properties that make it almost the perfect frame material. First, it is stiff. It does not flex under the loads a drone experiences, which means the arms hold their geometry precisely, and that directly affects flight performance. Second, it is light. Weight is the enemy in aviation, and carbon fiber lets engineers build a 5-inch racing frame that weighs under 50 grams. Third, it damps vibration relatively well. But carbon fiber has two weaknesses that every pilot needs to know. It is brittle, meaning under a sharp impact it does not bend, it snaps. And it conducts electricity. That second point matters a lot in drone building, because if a bare wire ever contacts the carbon fiber frame, you can short your electronics. Smart builders always use insulated wires or tape exposed pads. Plastic frames, usually ABS or polycarbonate, are cheap, forgiving, and light enough for small drones. Toy drones and entry-level beginner models use plastic frames extensively. When you crash a plastic frame, it might crack, but it rarely shatters the way carbon does. The downside is that plastic is heavier for the same stiffness, and for anything beyond recreational flying, plastic is simply not up to the job. Aluminium frames exist. You occasionally see them on older or commercial-grade platforms, but they are rare. Aluminium dents rather than cracks, which is useful, but it is heavier than carbon fiber for the same structural performance. It has largely been displaced. The most advanced drones use composite materials, combinations of carbon fiber with Kevlar or fiberglass, woven in at strategic points to add impact resistance while maintaining stiffness. Military drones especially use exotic composites. Now, let us talk about sizing, because this trips up almost every beginner. When you hear a drone called a 5-inch drone or a 7-inch drone, what do you think that means? Most people assume the frame itself is 5 inches wide, or 7 inches in some dimension. That is not what it means at all. The number refers to the propeller size the frame is designed to accommodate. A 5-inch frame is designed for 5-inch diameter propellers. The actual frame might be considerably larger or smaller than 5 inches in any single measurement. The size designation is a design specification. It tells you what propeller fits, and by extension, roughly what motors, battery, and performance envelope the drone is built around. This is important because the entire component selection process flows from this number. If you are building a 5-inch drone, you select motors appropriate for 5-inch props, an escape stack rated for the current those motors draw, and a battery sized to give you the flight time you want. Let me give you real examples. 3-inch drones are small, indecapable aircraft. They are typically used as sinew hoops, cinema-grade FPV drones with ducted propeller guards that protect both the props and whatever they fly near. You can fly a 3-inch sinew hoop inside a warehouse, a cathedral, a sports stadium. They are quiet, agile, and surprisingly smooth on camera. 5-inch drones are the workhorses of the FPV world. This is the size class that dominates racing and freestyle flying. The motors are powerful, the response is razor-sharp, and the frames are designed to survive crashes. Because in FPV racing, crashes are not exceptional events, they are just part of the workflow. If you are building a kit drone for a course like this one, it is almost certainly a 5-inch. 7-inch drones occupy an interesting middle ground. They are bigger, heavier, and carry larger propellers that generate more efficient lift. This makes them ideal for long-range cruising. A 7-inch long-range build might fly 15 to 20 kilometers from the pilot on a single battery, streaming video the entire way. 10-inch and above gets into heavy lift territory. Agriculture spraying drones, large mapping platforms, industrial inspection tools, these run large propellers driven by high-torque motors, and their frames are often entirely custom-engineered for the specific payload they carry. One more thing about frames worth mentioning: the mounting pattern. Most modern flight controllers and escape stacks mount using either a 20 x 20 mm or 30 x 30 mm bolt pattern. The frame you choose dictates which electronic stack you can install. Always check compatibility before you buy. Now we get to one of my favorite topics in the entire drone world: motors. Here is a question I want you to sit with for a moment. How does electricity become motion? Think about that. You have a battery, a thing that stores chemical energy. You have a wire, a conductor. And at the end of that wire, you have a motor that spins. How does that transition happen? How does chemical energy stored in a pack of cells become rotational mechanical force? The answer is electromagnetism. And it is one of the most elegant physical phenomena in all of science. Let me take you back to basics. When electric current flows through a wire, it creates a magnetic field around that wire. This is not a metaphor. It is a measurable, observable physical fact described by Ampere's law. The magnetic field circles the wire in a pattern you can predict with your right hand. Point your thumb in the direction of current flow, and your fingers curl in the direction of the magnetic field. Now take that wire and coil it into a loop. The magnetic fields from each section of the coil add together, creating a much stronger magnetic field through the center of the loop. Wind multiple loops together, and you have an electromagnet. Vary the current through that electromagnet, and you vary the strength and direction of the magnetic field it produces. This is the core principle of every electric motor. A motor has two fundamental parts: the stator and the rotor. The stator is stationary. It is the fixed part of the motor attached to the motor mount on the drone's arm. In a BLDC motor, the stator consists of iron core teeth wrapped with copper wire, forming the electromagnets we just described. The rotor is the rotating part. In a typical drone motor, what engineers call an outrunner configuration, the rotor is a bell-shaped housing that sits outside the stator and spins around it. Inside this bell, permanent magnets are bonded to the inner surface. These magnets are always magnetized. They create a constant magnetic field regardless of what the electronics are doing. Here is where the magic happens. If you energize the stator coils in a specific sequence, creating a rotating magnetic field, the permanent magnets in the rotor will try to align with that field. And as the field rotates, the magnets chase it. The rotor spins. Change how fast the field rotates, and the rotor speed changes. Reverse the rotation of the field, and the motor reverses direction. It is extraordinarily clean and controllable. Now, why do drones specifically use brushless DC motors? Why not just use a regular DC motor from a toy car? To understand this, let me explain what a brushed DC motor actually is. In a classic brushed motor, the rotor carries the coils of wire, and current is supplied to them through physical metal contacts called brushes that press against a rotating commutator ring. As the motor spins, different sections of the commutator connect to the power supply, switching the direction of current through the coils in sequence. The brushes are what perform the commutation, the switching. This works. It has worked for over 100 years. But it has critical limitations for drone applications. Brushes wear out. They are mechanical contact points that rub against the spinning commutator under high current loads. In a drone motor that spins at 20,000 RPM, brush wear is extreme. You can get a few hours of life out of a brushed motor before it starts degrading. Brushes create electrical noise. The physical contact introduces arcing, voltage spikes, and electromagnetic interference that can corrupt sensor data on the flight controller. Brushed motors are less efficient. The contact resistance of the brushes dissipates energy as heat, and at high speeds, the brushes simply cannot switch the current fast enough to maintain efficiency. A well-designed brushed motor peaks at around 60 to 70% efficiency. Now compare that to a brushless DC motor. There are no brushes. The commutation, the switching of current to create the rotating magnetic field, is done electronically by the escape. This electronic commutation has no moving parts, generates no mechanical wear, produces minimal electrical noise, and can switch fast enough to drive the motor at any speed we need. BLDC motors achieve 85 to 90% efficiency under typical operating conditions. They have no brushes to replace, no commutator to wear. A well-maintained BLDC motor can last for hundreds of hours. The limiting factors become the bearings and the insulation on the copper windings. And modern motors use ceramic bearings and high-temperature wire insulation that push service life dramatically. You might wonder about other motor types. What about stepper motors? Servo motors? Induction motors? Stepper motors are designed for precise positional control. They move in discrete steps and hold position accurately. But they are heavy for their power output, they have low torque at high speeds, and they are not designed for continuous high-speed operation. A drone motor might spin at 20,000 RPM under full throttle. A stepper motor would not survive that duty cycle. Servo motors are actually a category that includes BLDC motors in some classifications, but the traditional servo motor used in robotics has built-in position feedback and is optimized for positional control rather than speed. For driving a drone propeller, that feedback overhead is unnecessary. Induction motors, the kind used in industrial machinery, electric trains, and washing machines, work without permanent magnets, using induced currents in the rotor. They are extraordinarily efficient and reliable in large industrial sizes. But they are heavy, they need complex variable frequency drives, and they are simply not practical at the size and power levels needed for a small drone. Brushless DC with electronic commutation is the answer. It always has been for anything that needs to fly. Let me now explain something that every drone pilot hears, but many never fully understand: the kV rating. kV stands for kilovolts, except it does not mean kilovolts in the usual sense. In motor specification sheets, kV means RPM per volt. It is the ratio of motor speed to applied voltage measured at no load. A motor rated at 2400 kV, running on a fossil battery at 16.8 volts, will spin at approximately 2400 times 16.8, which is about 40,000 RPM at the shaft, with no propeller attached. Under load, with the propeller spinning air, that number drops substantially because the motor is doing work. Why does kV matter? A lower kV motor, say 1000 to 1500 kV, spins slower but produces higher torque. High torque means the motor can drive a large, heavy propeller efficiently. Agricultural drones, large survey platforms, delivery drones, these use low kV motors with big props. The large propeller moves a lot of air per revolution, which is efficient for carrying heavy payloads over long distances. A higher kV motor, 2000 to 2500 kV, for a typical 5-inch racer, spins faster, works with smaller props, and responds extremely quickly to throttle inputs. Racing demands rapid acceleration and deceleration. The drone needs to go from hover to full speed in milliseconds and back. High kV motors with mid-sized propellers deliver exactly that. Very high kV motors, 3000 kV and above, are found in ultra-competitive racing builds. Tiny props, screaming RPMs, brutal efficiency on sprint courses. But their power consumption is intense, and flight times are measured in minutes. Now let us talk about stator sizing, because this is another number that appears in every motor spec sheet. A motor labeled 2207 tells you two things. The stator diameter is 22 millimeters, and the stator height is 7 millimeters. The stator is the fixed core with the copper windings. A larger stator means more copper wire, more magnetic surface area, more torque, and more weight. A 2207 is physically larger and heavier than a 1806, but it can produce significantly more thrust before saturating. For a 5-inch freestyle or racing drone, a 2207 or 2306 motor is the standard choice. For 3-inch sinew hoops, something like a 1404 or 1507 is more appropriate. For 7-inch long-range drones, a 2806 or 3007 might be selected for its higher torque capability. And for professional platforms, DJI Mattress series, agricultural sprayers, delivery drones, military reconnaissance platforms, the motor selection becomes an engineering project in itself, balancing efficiency, torque, weight, heat management, and redundancy. The Escape electronic speed controller is the translator between the flight controller's intentions and the motor's actions. Here is the fundamental challenge. The battery in a drone is a DC source, direct current, flowing steadily in one direction at a fixed voltage. But a BLDC motor needs 3-phase AC alternating current, cycling through 3 separate windings in a precise rotating sequence. The Escape performs that conversion. Think of it this way. The flight controller is like a conductor in an orchestra. It knows the music and waves the baton, but it cannot play the instruments directly. The Escape is the musician. It takes the conductor's signal and translates it into the actual physical action of driving the motor windings. The Escape contains a set of power transistors, typically MOSFETs, arranged in what engineers call an H-bridge or 3-phase bridge configuration. These transistors switch on and off very rapidly, routing the battery current to the 3 motor windings in the precise sequence needed to create the rotating magnetic field. The switching frequency and timing determine both the motor speed and the efficiency of the conversion. Modern ESCs run switching frequencies of up to 48 kHz or higher. They're switching the motor phases tens of thousands of times per second. How does the flight controller tell the Escape what speed to run? This is where communication protocols come in. In the earliest drone ESCs, the signal was a PWM pulse width modulation. The Escape was trained to recognize a specific range of pulse lengths from around 1000 microseconds for zero throttle to 2000 microseconds for full throttle. The protocol was simple, it worked, and it was essentially borrowed from the model aircraft hobby. But it was slow. The update rate was limited to around 400 Hz, and it was vulnerable to electrical noise. Modern drones use D-Shot, a digital protocol that sends actual numerical throttle values as a digital packet rather than a timed analog pulse. D-Shot is immune to the noise issues of PWM, it is faster, and it supports bidirectional communication. The Escape can report back telemetry data like motor RPM and temperature to the flight controller. D-Shot 300, D-Shot 600, D-Shot 1200. The number refers to the data rate in kilobits per second. Now let me explain a configuration you will encounter constantly in drone building. The 4-in-1 Escape. A traditional setup uses 4 separate ESCs, one for each motor, wired individually. This works, but it is bulky and increases wiring complexity. A 4-in-1 Escape integrates the electronics for all 4 motors onto a single PCB, typically stacked directly under the flight controller in a standard 30x30 or 20x20 mm format. This dramatically simplifies the build, reduces weight, and improves heat management through the stack design. Most modern FPV drone builds use 4-in-1 stacks. Dedicated commercial platforms sometimes use individual ESCs for redundancy, or because the motor drives are physically distant from each other. One more feature worth understanding, the BEC or battery eliminator circuit. A drone battery might be running at 22 volts, but many onboard components, the receiver, the FPV camera, the video transmitter, need 5 volts or 12 volts. Instead of carrying a separate battery for those components, the BEC is a voltage regulator integrated into the Escape or power distribution board that steps the main battery voltage down to the regulated lower voltages. The BEC eliminates the need for a separate battery, hence the name. Let me trace the signal flow from pilot input to spinning motor because understanding this sequence is fundamental. You move a stick on your transmitter. The transmitter modulates a radio signal and broadcasts it. The receiver on the drone picks up that signal and decodes it, producing a digital data stream. That data stream goes to the flight controller over a UART or bus connection. The flight controller's processor, running at a loop rate of up to 8,000 times per second on modern hardware, reads that pilot input, compares it with what the IMU sensors are reporting about the drone's orientation and movement, runs the PID control algorithm, and calculates what throttle value each of the 4 motors needs. That throttle value is sent to the escape over D-shot. The escape switches its MOSFETs at exactly the right timing to drive the motor to that RPM. The motor spins. The propeller bites air. The drone moves. All of that, from your thumb moving to millimeters on the stick to the motor changing speed, happens in under 2 milliseconds. Every single cycle. 8,000 times per second. That is engineering. Now let us talk about power. The battery is the fuel tank, the fuel itself, and the engine all at once. Because unlike a combustion aircraft, in a drone the battery is not just storing energy, it is the only energy source. Everything electrical on that drone runs from the battery. The motors, the flight controller, the GPS, the video transmitter, the lights, the sensors, everything. Before I explain LiPo batteries specifically, I want to make sure everyone here has a solid intuition for the fundamental electrical concepts because they matter enormously in battery selection. Voltage is the electrical pressure, the potential difference that drives current through the circuit. Think of it like the pressure of water in a pipe. Higher voltage means more force pushing electrons through the wire. In drones, higher voltage allows us to spin motors faster or run them more efficiently. Current is the flow rate, the quantity of electrons moving past a point per second measured in amperes. Back to the water analogy, current is how many gallons per minute are flowing, not how much pressure is pushing them. Power is voltage times current. A drone motor drawing 10 amps at 22 volts is consuming 220 watts of power. 4 motors doing the same thing simultaneously, 880 watts. On a hard racing run or maximum throttle hover, a competition FPV drone can draw to 2,000-3,000 watts. Energy is power multiplied by time. A battery holding 22 watt-hours can supply those 880 watts for about 90 seconds at maximum draw, which is about right for an aggressive FPV race run. Now, why lithium? Lithium polymer batteries, LiPo, dominate the drone world for a handful of reasons that become clear once you compare them to alternatives. Lead-acid batteries are heavy, robust, and cheap. Car batteries are lead-acid. They can deliver enormous current. But the energy density, the amount of energy stored per kilogram, is terrible. A car battery weighs 15 kilograms. A LiPo pack with the same stored energy might weigh 1 kilogram. Lead-acid is a non-starter for any aircraft. Nickel metal hydride batteries, NiMH, were the standard for RC aircraft before lithium chemistry arrived. They are safer, more tolerant of abuse than LiPo, and environmentally friendlier. But their voltage per cell is lower, their energy density is lower, and their internal resistance is higher. NiMH simply cannot deliver the current spikes that drone motors demand. Lithium-ion, the chemistry in your phone and laptop, has excellent energy density. A lithium-ion 18650 cell, the cylindrical cell in laptop battery packs and in Tesla vehicles, can hold 200 to 260 watt-hours per kilogram. But lithium-ion cells are optimized for energy density rather than power density. They have relatively high internal resistance and cannot deliver the enormous burst currents that a racing drone demands. Some long-range and survey drone platforms do use lithium-ion because flight time matters more than burst power, and the DJI Mavic series uses lithium-ion chemistry for exactly this reason. Lithium iron phosphate, LiPo4, is an emerging chemistry that offers exceptional safety, very long cycle life, and excellent performance at high temperatures. The downside is lower energy density than standard LiPo. Military and industrial drones are beginning to explore LiPo4 for applications where reliability and safety outweigh raw performance. For high-performance drones, racing, freestyle, photography requiring aggressive maneuvers, lithium polymer remains king. Why? LiPo cells combine very high energy density with very low internal resistance, allowing them to deliver enormous burst currents. A typical racing LiPo can discharge at 100 times its capacity in a fraction of a second. The voltage per cell is 3.7 nominal, with a fully charged voltage of 4.2 and a minimum safe discharge voltage of around 3.5. Let us decode a real battery label together. Take a pack labeled 4S 1500 mAh R100C. The 4S means 4 cells connected in series. Series connection adds voltages together. 4 cells at 3.7 volts nominal gives you 14.8 volts nominal. At full charge, 4 times 4.2 is 16.8 volts. This is a 4-cell pack, universally referred to as 4S. 1500 mAh is the capacity 1500 milliamperes, or 1.5 amperes. This tells you the total charge stored. If the pack delivers 1.5 amps for 1 hour, it is fully discharged. If it delivers 150 amps for 36 seconds, same result. Capacity does not change with current draw. The total charge is fixed. 100C is the discharge rating. The C rating is a multiplier of the capacity. 100C means the pack can theoretically deliver 100 times its capacity in amps. 100 times 1.5 equals 150 amps continuous maximum. In practice, manufacturers are somewhat optimistic with C ratings, but the principle is sound. A higher C rating indicates lower internal resistance and greater ability to deliver burst current. The stored energy can be calculated as voltage times capacity. 14.8 volts times 1.5 amperes equals 22.2 watt-hours. That is the theoretical maximum energy available from this pack. Now let us talk about cell configurations, because this confuses beginners constantly. When batteries are connected in series, stacking them end to end like a batteries in a torch, the voltages add and the capacity stays the same. 4S means 4 cells in series. You can also connect cells in parallel, positive to positive, negative to negative. This keeps the voltage the same but adds the capacities. A4S2P pack has 4 cells in series, with each cell position actually being to cells in parallel. This gives you the same voltage as a standard 4S, but double the capacity and double the current capability. The S number tells you the voltage. The P number tells you how many cells are in parallel. Most FPV racing packs are 4S or 6S. 6S packs, 6 cells in series at 22.2 volts nominal, have become increasingly popular for racing because higher voltage allows motors to run more efficiently for the same power output, reducing heat and extending motor life. Industrial and military platforms use much higher cell counts. A large hexacopter delivery drone might run a 12S or even higher configuration. Some VTOL hybrid aircraft with larger battery systems use custom high-voltage packs designed specifically for that platform. Let me now talk about safety, and I cannot stress this enough. LiPo batteries are powerful and they are unforgiving. Every year, fires from mishandled LiPo batteries destroy workshops, cars, homes, and occasionally aircraft. Understanding LiPo safety is not optional. Thermal runaway is the term for what happens when a lithium cell goes wrong. When a lithium cell is damaged, overcharged, shorted, or exceeds its temperature limits, an exothermic chemical reaction begins. The reaction generates heat. That heat accelerates the reaction. The accelerating reaction generates more heat. Within seconds, the cell can reach temperatures above 500 degrees Celsius and begin ejecting burning electrolyte. In a multi-cell pack, one cell going into thermal runaway can trigger adjacent cells, and you can go from a small problem to a fully involved fire in under 30 seconds. Lithium fires cannot be extinguished with water. Water reacts violently with burning lithium, producing hydrogen gas and making things dramatically worse. Lithium fires are Class D fires. You smother them with dry sand, lithium-specific fire blankets, or Class D extinguisher. Some pilots keep a bucket of dry sand at their charging station. It is not a bad idea. The rules for LiPo safety are non-negotiable. Never puncture, crush, or deform a pack. Never charge above 4.2 volts per cell. Never charge at a rate higher than the pack's rated C value. Never leave a charging pack unattended. Never store a pack at full charge. LiPos should be stored at around 3.8 to 3.85 volts per cell, a condition called storage voltage. Modern smart chargers have a storage charge mode that will charge or discharge a pack to storage voltage automatically. If a pack becomes swollen, puffy, bulging, noticeably thicker than normal, it is damaged. The electrolyte has broken down and is producing gas. Do not fly a swollen pack. Do not charge it. Discharge it safely, dispose of it as electronic waste, and replace it. When flying commercially or transporting packs on aircraft, airline regulations apply. International aviation rules limit lithium battery carry-on quantities and watt-hour ratings. Packs above 100 watt-hours require airline approval. Packs above 160 watt-hours are generally prohibited in passenger aircraft cabins. If you are traveling to fly commercially, research the specific regulations for your route before you pack your gear. Looking toward the future, solid-state batteries. These replace the liquid electrolyte in current lithium cells with a solid ceramic or polymer electrolyte. Solid-state batteries promise dramatically higher energy density, significantly improved safety. No flammable liquid electrolyte means thermal runaway is far less likely, and longer cycle life. Several companies are working on solid-state battery packs for aviation applications. When they arrive at commercial scale, they will fundamentally change drone endurance. A delivery drone that currently flies for 30 minutes might fly for 90 minutes on a solid-state pack of the same weight. The military implications are equally significant. The flight controller is the brain of the drone. If you removed the flight controller and tried to fly, the drone would not just fly badly. It would crash within a fraction of a second. The motors would have no coordination. The propellers would generate forces in random directions, and the drone would tumble. The flight controller takes the pilot's intentions, combines them with sensor data about what the drone is currently doing, and calculates precisely what each motor needs to do at this exact moment. It does this calculation thousands of times per second. It is the fastest responder on the drone. Most modern flight controllers use processors from two main families. The STM32 family, made by STMicroelectronics, is the standard for FPV drones. These are ARM Cortex-M processors running at hundreds of megahertz with hardware floating point units. The F405, F722, and H743 variants are popular choices, with the H743 representing current state-of-the-art for high-performance FPV. The ESP32, made by Espressif, is a dual-core processor with built-in Wi-Fi and Bluetooth. It is commonly used in low-cost and long-range drone systems, and it is the processor in platforms like the Express LRS radio system hardware. The flight controller runs what is called a control loop, a continuously repeating cycle of sense, compare, and correct. Sense what the drone is doing. Compare it to what the pilot commands. Correct the motor outputs to reduce the difference. Loop. Loop again. 8,000 times per second. At the heart of this loop is a PID controller, proportional, integral, derivative. This is the algorithm that makes drones flyable. We will go deep into PID control in Chapter 3, But for now, understand that PID is the mathematical framework that converts the difference between desired and actual flight state into motor commands. It is elegant, it is powerful, and tuning it well is what separates a drone that flies smoothly from one that oscillates, wobbles, and feels mushy. The flight controller also integrates sensor data from the IMU, the Inertial Measurement Unit, and that is our next major topic. Because without the IMU, the flight controller is blind. Imagine closing your eyes and having someone slowly tilt you to one side. Even with your eyes closed, you know you are tilting. You can feel it. You adjust your balance. How? Your inner ear. Specifically, the vestibular system, a collection of fluid-filled canals and tiny hair cells that sends both rotation and linear acceleration. It is one of the most sophisticated sensing systems in biology, and it is almost exactly what drones replicate with their IMU. The IMU, Inertial Measurement Unit, is the drone's inner ear. It tells the flight controller which direction is down, how fast the drone is rotating, which way it is pointing, and whether it is accelerating or decelerating. Without the IMU, the flight controller cannot know if the drone is level, inverted, banking, or spinning. There is no flight without the IMU. A modern drone IMU contains 3 sensors integrated into a single tiny chip: an accelerometer, a gyroscope, and sometimes a magnetometer. Let me explain each one in depth. The gyroscope measures angular velocity, the rate of rotation around an axis. Not position, not tilt angle. Rate of rotation. There are 3 rotation axes in 3-dimensional space. Roll is rotation around the front-to-back axis, the drone tilting left or right like a boat rolling in waves. Pitch is rotation around the left-to-right axis, the nose coming up or going down. Yaw is rotation around the vertical axis, the drone spinning like a compass needle, changing the direction it faces. These 3 axes and the angular velocity around each of them are what the gyroscope measures. Modern drone gyroscopes do not use the spinning mechanical gyroscopes of old navigation systems. They use MEMS technology, microelectromechanical systems, which implements the gyroscope function using microscopic silicon structures etched into a chip. The MEMS gyroscope works through the Coriolis effect. The Coriolis effect is a physical phenomenon that occurs when a vibrating object is rotated. A vibrating structure experiences a force perpendicular to both its direction of vibration and the axis of rotation. This Coriolis force is tiny but measurable. Inside the MEMS gyroscope, there is a tiny vibrating mass, a microscopic tuning fork structure, vibrating at a precisely controlled frequency. When the chip is rotated, the Coriolis force causes the vibrating mass to deflect slightly in a perpendicular direction. That deflection changes the electrical capacitance between the moving mass and fixed sense plates. The chip measures this capacitance change and converts it to an angular velocity reading. For each of the 3 axes, roll, pitch, and yaw, there is a separate sensing structure. The chip integrates all 3 into a single package, giving you 3-axis angular velocity at sample rates of up to 32 kHz on modern chips like the ICM4 to 688 and BMI to 70. The flight controller integrates the angular velocity over time. Mathematically, integration of angular velocity gives you angle to track the drone's orientation. If the gyroscope says the drone is rolling at 300 degrees per second, and that has been happening for 100 milliseconds, the drone has rolled 30 degrees. The flight controller knows this instantly and corrects the motor outputs before you or I would even perceive the motion. The accelerometer measures linear acceleration, not velocity, not position, but rate of change of velocity. But here is the fascinating part. The accelerometer also measures gravity. Gravity is, from the perspective of the accelerometer, simply a constant acceleration. When the drone is sitting perfectly level on a table, the accelerometer reports 1 g of acceleration pointing straight down. This is the drone feeling the ground pushing up against gravity. It is equivalent to what your feet feel when you stand. The floor pushes up, you feel weight. When the drone tilts, the accelerometer reading changes. At a 45-degree bank, the vertical component of gravity felt by the sensor decreases and a horizontal component appears. By measuring how the gravity vector distributes across the three axes, the accelerometer can determine the drone's tilt angle in both the roll and pitch directions. This is different from what the gyroscope does. The gyroscope tells you how fast you are rotating. The accelerometer tells you where down is, your absolute orientation with respect to gravity. The MEMS accelerometer works through a proof mass and capacitive sensing system. A tiny microscopic mass, the proof mass, is suspended between fixed capacitor plates by even tinier silicon springs. When the chip accelerates, the proof mass lags behind due to inertia, just like you are pushed back into your seat when a car accelerates. This displacement of the proof mass changes the gap between it and the fixed plates, changing the electrical capacitance. The chip measures this change and converts it to acceleration. The proof mass is genuinely tiny. We are talking about structures measured in micrometers, etched into a silicon wafer using photolithography processes borrowed from semiconductor manufacturing. The entire sensing element might be a few hundred micrometers across. The fact that this microscopic structure can reliably measure gravity and acceleration, and that you can mass-produce it for a fraction of $1, is a triumph of modern engineering. The magnetometer is essentially a digital compass. It measures the direction and strength of the local magnetic field. Earth has a global magnetic field generated by the churning molten iron in the outer core, roughly analogous to a giant bar magnet tilted slightly relative to the rotation axis. This field extends throughout the planet and into space. On the surface, it points generally toward magnetic north, and it has a predictable strength and inclination at every location on Earth. By measuring the direction of this field, the magnetometer gives the drone its heading, which direction is north, and by extension, which direction the drone is facing. This is essential for GPS-based flight modes. When the flight controller knows the drone's heading, it can fly waypoint missions, return to home, and hold a position accurately even in wind. Without heading information, the drone cannot translate GPS coordinates into motor commands. It does not know which way to push to move north. However, magnetometers have a critical vulnerability: electromagnetic interference. Any local magnetic field, from motors, from escape current, from power wires, overlays on top of Earth's magnetic field and distorts the reading. On a drone, you have 4 powerful motors, 4 ESCs, and high current power leads, all of them generating significant magnetic fields when operating. For this reason, the magnetometer is typically placed as far from the power electronics as possible, often in the GPS unit mounted on a mast above the frame, getting physical separation from the interference sources. Even so, magnetometer calibration is required before flight, and some flight controllers perform continuous calibration routines to track and compensate for learned interference patterns. Near high-voltage power lines, the magnetometer becomes essentially useless. The electromagnetic field from the transmission line completely overwhelms Earth's faint background field. Experienced pilots know to recalibrate the magnetometer after flying near power infrastructure. Here is the key insight that took aerospace engineers decades to fully implement. No single sensor is good enough. Every sensor has limitations. The gyroscope is extremely fast and precise at measuring rotation, but it drifts. Integration errors accumulate over time. If you start with perfect knowledge of orientation and integrate the gyro measurements, within minutes, the calculated orientation has drifted significantly from reality. The gyroscope cannot tell the difference between a real rotation and the slow accumulation of numerical error. The accelerometer is excellent at detecting gravity, but it also detects every vibration, every jolt, every air turbulence. On a drone with 4 rapidly spinning motors, the accelerometer signal is noisy. It is useful for slow orientation estimation, but too noisy for rapid flight control. The magnetometer gives absolute heading, but is vulnerable to interference and gives no information about roll and pitch. GPS gives absolute position and, with sufficient velocity, heading, but it updates slowly at 1 to 10 Hz and is unavailable indoors or underground. The solution is sensor fusion, combining multiple imperfect sensors in a mathematically principled way to produce an estimate better than any individual sensor could provide. The workhorse of sensor fusion in drones is the Kalman filter, developed by Rudolf Kalman in 1960 and first applied to navigation in the Apollo program. The Kalman filter maintains a mathematical model of the system state, in this case, orientation, position, and velocity, along with an estimate of the uncertainty in that state. At each time step, it does two things. It predicts the next state based on the physics of motion, and it corrects that prediction using new sensor measurements, weighted by how much it trusts each sensor relative to the predicted uncertainty. Practically, this means trust the gyroscope in the short term because it is fast and precise, but over long intervals, correct for drift using the accelerometer, and GPS trust the accelerometer for slow tilt estimation, but filter out the high-frequency vibration noise. Use GPS to anchor position absolutely, but smooth out the jumpy GPS updates with a much faster inertial sensors. The analogy I find most helpful. Imagine you are navigating a city on foot and you have three sources of information. You have a pedometer that counts your steps, very precise for short distances, but after a long walk the accumulated error is significant. You have a compass that gives you heading reliable in open areas, but confused near large buildings. And you have occasional GPS map checks, very accurate, but you can only check every minute or so. A skilled navigator combines all three, mostly trusting the step count and compass for smooth, continuous navigation, but using the GPS checks to correct accumulated errors. The Kalman filter is the mathematical implementation of exactly this strategy. The result is an orientation and position estimate that is smooth, fast, and accurate, exploiting the strengths of each sensor while compensating for each sensor's weaknesses. This is what makes stable, GPS-assisted drone flight possible. Most people think GPS and GNSS are the same thing. They are not. GPS, Global Positioning System, is a specific constellation of navigation satellites operated by the United States Department of Defense. It was developed starting in the 1970s, became fully operational in 1995, and for many years was the only practical satellite navigation system available to civilian users. GPS became so dominant and so ubiquitous that its name became synonymous with satellite navigation in general, in the same way that Xerox became synonymous with photocopying or Google became synonymous with searching the internet. GNSS, Global Navigation Satellite System, is the umbrella term for all satellite navigation constellations. GPS is one GNSS, but there are 5 others currently operational and a 7th in development. Let me introduce them all. GPS, operated by the United States Air Force. 31 active satellites in medium Earth orbit at an altitude of approximately 20,200 kilometers, inclined at 55 degrees to the equator. Transmits on the L1 frequency at 1,575.42 MHz and L2 at 1,227.60 MHz, with L5 being added for civilian aviation use at 1,176.45 MHz. GLONASS, the Russian counterpart to GPS, originally developed by the Soviet Union in the 1970s and rebuilt by the Russian Federation following its degradation after the Soviet collapse. 24 satellites at 19,100 kilometers altitude. Uses slightly different frequencies from GPS, but provides comparable global coverage. Galileo, Europe's independent GNSS, developed by the European Union and European Space Agency. Galileo is notable for being a civilian-first system, unlike GPS, which was always military primary, with civilian access added later. Galileo transmits on L1E5A, E5B, and E6 frequencies and promises higher accuracy than GPS for civilian users. BeiDou, China's GNSS, originally a regional system and now expanded to global coverage. 35 satellites in a combination of medium Earth orbit, inclined geosynchronous orbit, and geostationary orbit. The geostationary component gives BeiDou particularly good coverage in the Asia-Pacific region, including India. BeiDou is notable for including a short message communication service built into the navigation signal. NavIC, we will discuss this in its own dedicated section. But briefly, India's regional navigation satellite system, operated by ISRO, providing high-accuracy coverage over India and 1,500 kilometers around it. QZSS, Japan's quasi-zenith satellite system, designed to enhance GPS coverage in Japan and surrounding regions by maintaining satellites in highly elliptical orbits that spend most of their time nearly overhead Japan, the zenith in the name. QZSS transmits compatible signals to GPS, acting as an augmentation rather than a fully independent system. Now, how does any satellite navigation system actually work? The fundamental principle is deceptively simple: measuring time. Each satellite carries an extremely precise atomic clock, typically a cesium or rubidium atomic clock, accurate to about 1 nanosecond over several hours. Each satellite continuously transmits a radio signal containing two pieces of information: the exact time the signal was sent and the satellite's current position in space. Your GNSS receiver in your drone, your phone, your car picks up this signal and notes the time it arrived according to the receiver's own clock. The difference between the transmission time and the arrival time, multiplied by the speed of light, gives the distance to that satellite. Light travels approximately 300 million meters per second, so a timing error of 1 nanosecond translates to 30 centimeters of distance error. This is why atomic clocks are necessary. The timing requirements are extraordinary. With a distance to one satellite, your receiver knows you are somewhere on a sphere centered on that satellite with that radius. With a distance to two satellites, you are somewhere on the circle where those two spheres intersect. With a distance to three satellites, you are at one of two specific points where the three spheres intersect, and usually one of those points is clearly on or near Earth's surface. The other is in deep space. With a distance to 4 satellites, you can solve for 4 unknowns: latitude, longitude, altitude, and, crucially, receiver clock error. The 4th satellite is required because the receiver's clock is not an atomic clock. It is a quartz oscillator, and it drifts. The mathematics of GPS uses the 4th satellite measurement to solve for the clock offset and correct it simultaneously with the position solution. This process is called trilateration, not triangulation. Triangulation uses angles. Trilateration uses distances. The distinction matters technically even if the terms are often confused in casual use. The quality of a GNSS fix is described by several metrics. Satellite count is the simplest. More satellites always means better redundancy and accuracy. A minimum of 4 is required for a 3D fix. Professional survey and precision drone operations target 8 or more simultaneously visible satellites for maximum accuracy. DOP, horizontal dilution of precision, describes the geometric quality of the horizontal position solution. If all visible satellites are clustered in one part of the sky, the position solution is geometrically weak and DOP is high. If satellites are spread evenly across the sky, all directions are well constrained and DOP is low. DOP below 1.5 is considered excellent. DOP above 2.5 indicates poor satellite geometry and reduced accuracy. PDOP, position dilution of precision, is the 3-dimensional equivalent, combining both horizontal and vertical geometric quality. The signals that satellites transmit travel through space and then through the Earth's atmosphere before reaching your receiver. And the atmosphere introduces errors. The ionosphere, a layer of electrically charged particles between roughly 60 and 1000 kilometers altitude slows down radio signals slightly. The amount of slowing depends on the frequency of the signal and the electron content of the ionosphere, which varies with time of day, season, solar activity, and geographic location. This ionospheric delay is one of the primary sources of error in single-frequency GNSS. GPS originally transmitted one civilian signal, L1, at 1575.42 MHz. This was sufficient for most applications, but the ionospheric delay introduced errors of up to 10 meters under adverse conditions. The solution is to transmit on multiple frequencies. The ionospheric delay is frequency dependent. It affects different frequencies by different amounts. By comparing the same signal received on two different frequencies, the receiver can mathematically calculate and remove the ionospheric delay. This dual frequency correction can reduce ionospheric errors by 90% or more. Modern GPS transmits on L1, L2, and L5. Galileo transmits on E1, E5A, E5B, and E6. A dual-frequency GNSS receiver, one that can receive and process two frequency bands simultaneously, achieves dramatically better accuracy than a single-frequency receiver. This brings us to RTK, real-time kinematic positioning. Standard GNSS gives you meter-level accuracy, good enough for navigation and general position holding, but not good enough for professional survey, precision agriculture, or construction site mapping. RTK is a technique that achieves centimeter-level accuracy in real time by using a reference station. The reference station is placed at a precisely known survey point. Its exact coordinates are known to millimeter accuracy. The reference station receives the same GNSS signals as the drone receiver, calculates the errors in those signals by comparing the measured position to the known position, and broadcasts correction data to the drone in real time over a radio link. The drone's RTK receiver applies these corrections to its own position measurement, and the result is position accuracy of 1 to 2 centimeters horizontally and 2 to 3 centimeters vertically. This level of accuracy transforms what drones can do. For aerial survey and mapping, RTK accuracy means the photogrammetric outputs, the 3D models, and orthomosaic maps generated from drone imagery can be used for engineering-grade measurements without the need for ground control points. For precision agriculture, RTK means the drone can follow field boundaries and flight lines with centimeter precision, maximizing coverage efficiency and minimizing overlaps. For corridor mapping, roads, railways, pipelines, power lines, RTK enables accurate measurement of infrastructure condition across hundreds of kilometers. PPK, post-processing kinematic, is the offline equivalent. The drone logs its raw GNSS observations during flight, and the corrections are applied afterwards using data from a reference station. PPK can be more accurate than real-time RTK because the correction algorithm can look both forward and backward in time, and because you are not dependent on a real-time radio link. PPK is common in professional survey operations. The DJI Phantom 4 RTK, the Autel EvoMax 4T the SenseFly EB. These are examples of professional drone platforms with integrated RTK GNSS. In the mining industry, RTK drones have largely replaced conventional surveying teams for volumetric calculations, measuring stockpiles, tracking excavation progress, monitoring terrain change. A task that once took a team of surveyors to days can be completed by one operator with a drone in 2 hours with comparable or better accuracy. You have GPS in your smartphone. Your drone has GPS. Are they the same? No. They are fundamentally different in capability. And understanding the differences helps you understand why professional drones cost what they cost. Your smartphone GPS uses a single frequency receiver, typically L1 only. It has a small antenna designed to fit into a thin slab of glass and aluminium. The receiver is optimized for power consumption rather than accuracy because it shares battery with a cellular radio, a screen, and dozens of other systems. Under ideal conditions in open sky, your phone GPS can achieve 3 to 5 meter horizontal accuracy. In urban canyons, under tree cover, or during periods of high ionospheric activity, accuracy can degrade to tens of meters. A consumer drone GPS, like the module in a DJI Mini 4 Pro or a Mavic 3, uses a multi-constellation receiver, typically receiving both GPS and GLONASS, sometimes also Galileo and BeiDou. With more satellites in the solution, accuracy improves and reliability increases. Under good conditions, a consumer drone GPS achieves 1 to 3 meters horizontal accuracy. A professional survey drone GPS, like the DJI Phantom 4 RTK or the Trimble ZX5, uses a dual-frequency, multi-constellation RTK receiver with a high-quality patch antenna designed specifically for aircraft use. With RTK corrections, this achieves 1 to 2 centimeter horizontal accuracy in real time. The hardware cost alone for an RTK GNSS module is in the range of several $1,000s. An industrial or military drone GNSS might use triple-band receivers, simultaneously receiving L1, L2, and L5, combining GPS, GLONASS, Galileo, BeiDou, and NavIC for the maximum possible satellite count and the most accurate ionospheric correction. These systems can achieve sub-centimeter accuracy under survey conditions. The practical implication for drone pilots: a consumer drone's GPS is accurate enough to hold position within a few meters and to safely perform return to home. It is not accurate enough for professional survey work. If you are building a survey business, invest in RTK. Let us talk about NavIC, India's own navigation satellite system, and why its existence matters enormously. NavIC stands for Navigation with Indian Constellation. Its formal name is the Indian Regional Navigation Satellite System, or IRNS. It is operated by the Indian Space Research Organisation, ISRO. Why did India build NavIC? This is the question at the heart of the system, and the answer is strategic. In 1999, during the Kargil War between India and Pakistan, the Indian military requested detailed GPS data for the Kargil region from the United States. The request was denied. The US military, at that time, could restrict GPS access for non-allied nations in specific regions. India was conducting military operations in territory it needed to navigate precisely, and the navigation data was controlled by a foreign power that chose not to share it. That experience, the vulnerability of dependence on foreign navigation infrastructure at a critical moment, motivated India to develop its own sovereign navigation system. NavIC is the result. The initial constellation of 7 satellites was launched between 2013 and 2018. 4 satellites are in geostationary orbit, fixed positions over the equator, and 3 are in geosynchronous orbit inclined at 29 degrees, giving coverage that extends from approximately 30 degrees south to 50 degrees north latitude and 40 degrees to 140 degrees east longitude. This covers all of India and extends 1,500 kilometers beyond its borders. NavIC operates on the L5 band at 1,176.45 MHz and the S band at 2,492.028 MHz. The L5 band has an interesting advantage over the GPS L1 band. It experiences less ionospheric interference because higher frequency L1 signals are more significantly delayed by the ionosphere than L5. NavIC's L5 signal can achieve better accuracy in the equatorial region where India sits compared to GPS L1 only receivers. NavIC's strategic importance goes beyond navigation. In a conflict scenario where an adversary with the capability to jam or deny GPS tries to disable India's navigation infrastructure, NavIC provides an independent backup. Military drones, precision-guided munitions, naval vessels, and land vehicles equipped with NavIC receivers continue to navigate accurately even if GPS is unavailable. On the civilian side, NavIC is increasingly used by Indian Railways for train tracking, by disaster management agencies for emergency response coordination, and by fishing vessels for navigation in Indian territorial waters. Modern smartphones are beginning to incorporate NavIC. From the Snapdragon 720G chipset onward, Qualcomm's mobile processors support NavIC. The iPhone 15 series added NavIC support. As more devices add NavIC alongside GPS and Galileo, position accuracy in India will improve substantially, particularly in equatorial regions where GPS ionospheric errors are historically larger. For the Indian drone industry, NavIC offers a path to navigation independence. Future military UAVs and commercial drones operating under DGCA regulations will likely be required to support NavIC as the government expands the system's coverage and application. This is a topic I want to approach carefully. We are not here to glorify violence or celebrate the tools of warfare, but we cannot have an honest, complete conversation about drones in the 21st century without acknowledging that the battlefield has been completely transformed by unmanned aerial systems, and understanding that transformation is essential for anyone serious about the drone industry. What is happening in Ukraine has been called the first drone war, which is not entirely accurate historically, since drone warfare has been ongoing since the early 2000s, but it is the first conflict where drone technology at every level, from consumer to military, has been deployed at scale by both sides simultaneously. FPV drones, the same 5-inch racing drones we have been discussing, have become primary weapons. Modified with small explosive charges and flown by operators wearing FPV goggles, they are used for direct attack on vehicles, equipment, and personnel. The cost of a combat-configured FPV drone can be as low as a few $100s. The cost of the armored vehicle it might disable is millions. This asymmetry has fundamental implications for how modern armies procure and deploy equipment. Reconnaissance drones, including consumer DJI Mavic and Mattress platforms on both sides of the conflict, have transformed tactical awareness. A single small drone with a decent camera can observe an entire village square from 500 meters altitude, invisible and nearly silent. Artillery can be directed within seconds of observation. Movement of troops and vehicles cannot be hidden from even a basic commercial drone. Loitering munitions, sometimes called kamikaze drones or suicide drones, are a distinct category. These are aircraft designed to loiter over a target area until a suitable target presents itself, then dive and detonate. The Shart 136 used extensively in the conflict, the Switchblade family used by Ukrainian forces, the Harop operated by Israel, these are all loitering munitions. They combine the persistence of a surveillance platform with the lethality of a guided munition. Electronic warfare has become the dominant counter-drone tool. GPS jamming, broadcasting noise on GPS frequencies to prevent receivers from acquiring satellite signals, is ubiquitous near the front lines. Areas with active electronic warfare jamming are effectively GPS denied. Drones that rely on GPS for navigation become uncontrollable or return to home if GPS lock is lost. GPS spoofing takes this further. Rather than blocking GPS, spoofing involves transmitting false GPS signals, precisely constructed fake signals that convince a receiver it is somewhere it is not. A drone navigating by GPS in a spoofed environment might follow its programmed waypoints faithfully, believing it is on course, while actually flying in a completely different direction determined by the spoofer. We will go into more detail on spoofing shortly. Fiber optic drones represent a counter to both jamming and spoofing. Instead of radio control links, the drone is connected to the operator by a thin optical fiber spool. The control signal travels as light through the fiber, immune to radio frequency jamming, impossible to spoof remotely, with no electromagnetic emissions to intercept or track. The practical limitation is range. You can only unspool so much fiber. But for close-range precision strikes and surveillance, fiber optic drones are increasingly attractive for military applications. Drone swarms represent perhaps the most significant emerging military drone technology. Rather than a single capable drone, A swarm consists of many simpler drones coordinating their actions collectively. A swarm of 50 small drones can saturate counter-drone defenses, overwhelm a target with simultaneous threats from multiple directions, and achieve area denial over large zones. Chinese military demonstrations, Israeli research programs, and various US Department of Defense projects have all demonstrated swarm capabilities. The defense challenge is that traditional air defense systems designed for individual aircraft struggle against dozens of simultaneously incoming threats. Counter-drone systems have evolved rapidly in response. Radio frequency detection systems scan for the control links of commercial drones. Optical and thermal systems detect the visual or thermal signatures. Jamming systems disrupt control frequencies. Hardkill systems, kinetic weapons from modified shotguns to high-energy lasers, physically destroy incoming drones. The DroneGun Tactical, the Dedrone drone tracker, the Rafale drone dome, these are examples of the growing counter-drone industry. The Iran-Israel conflict has showcased additional dimensions. Iran's use of Shahad series loitering munitions in attacks on Israeli territory, and Israeli use of sophisticated drone-based reconnaissance and strike capabilities represents a new kind of strategic drone exchange between states with significant technical capability. The Red Sea conflict and Houthi drone and missile attacks on shipping have demonstrated that even non-state actors can deploy sophisticated unmanned systems that challenge naval defenses, costing orders of magnitude more. The lesson that military planners, drone engineers, and policymakers are all absorbing simultaneously is this: drone technology has fundamentally disrupted the traditional economics of military power projection. Small, cheap, numerous, and increasingly autonomous, drones are changing every dimension of conflict. Let us go deeper on GPS spoofing, because it is not just a military problem. It affects civil aviation, maritime navigation, and drone operations in contested or high-security environments. Spoofing works by transmitting a counterfeit GPS signal that is stronger than the genuine satellite signal. The GPS receiver, which cannot inherently distinguish a genuine satellite signal from a well-constructed fake, locks onto the stronger counterfeit signal and calculates a position based on it. The spoofer controls the fake signal to report whatever position it wants the receiver to believe. The implications are serious. A drone navigating by GPS in a spoofed environment might be told by its GPS receiver that it is precisely on its programmed flight path, while the actual drone is somewhere entirely different, perhaps crossing into restricted airspace, approaching a sensitive installation, or simply flying off course over terrain it was not programmed to navigate. The drone's autopilot has no way to know the GPS is lying. Sophisticated spoofing attacks are gradual. Rather than suddenly jumping the receiver to a fake position, which might trigger the autopilot's anomaly detection, the spoofer slowly walks the reported position away from reality, a few meters at a time, while the drone tracks faithfully, unaware it is being guided. Real-world examples include interference events over the Black Sea, where ships reported GPS positions, placing them inland at airports. GPS position anomalies around Moscow have been extensively documented. In the Middle East, aviation authorities have issued warnings about GPS interference affecting hundreds of commercial aircraft per month in some regions. Detection is challenging. Some approaches include comparing GPS position to an independent position estimate from an inertial navigation system, from optical flow, from terrain matching. A sudden divergence between GPS and independent position indicates potential spoofing. Multi-constellation GNSS receivers are more robust, spoofing GPS alone while simultaneously spoofing GLONASS, Galileo, and BeiDou coherently is dramatically harder than spoofing a single constellation. A receiver that cross-checks across constellations is more resistant. Authentication, cryptographic signing of GNSS signals, is the ultimate solution. Galileo's Open Service Navigation Message Authentication, called OSNMA, provides cryptographic authentication of the satellite signal, making it impossible to forge without the satellite's private key. GPS is developing similar civilian authentication for L1C and L5 signals. When these authentication mechanisms are widely deployed, spoofing will become dramatically harder. Fiber optic control links, as we discussed, remove the radio control vulnerability entirely. Visual navigation, using cameras and image processing to navigate by recognizing and tracking visual landmarks, provides a GPS-independent navigation capability. Terrain matching, correlating elevation profiles measured by radar or LiDAR to a preloaded terrain database, is used in cruise missiles and advanced military drones to navigate accurately without any satellite signal. How does a drone know how high it is? GPS gives you altitude, but GPS altitude is measured from an ellipsoidal model of the Earth's shape, not from the actual ground below you. GPS altitude can be off by 10 to 20 meters compared to geometric height above the takeoff point. And GPS altitude updates at only 1 to 10 Hz, which is far too slow for flight control. The barometer solves this. Atmospheric pressure decreases predictably with altitude. At sea level, standard atmospheric pressure is 1013.25 hectopascals. For every 8.5 meters of altitude gain, pressure drops by approximately 1 hectopascal. By measuring atmospheric pressure continuously, the flight controller can track altitude changes with centimeter-level resolution and at update rates of hundreds of hertz. The key operational detail: the barometer measures relative altitude. At takeoff, the flight controller records the ambient pressure as the zero reference. All subsequent altitude readings are expressed as pressure change from that reference, converted to meters. This is why a drone's flight controller altitude display shows 0 meters immediately before takeoff, regardless of whether you are at sea level or at 5,000 feet above sea level in a mountain valley. The most commonly used barometric sensors in drones are the BMP-280, cheap, accurate to about 1 meter, widely used in consumer drones, the MS-5611, which offers better resolution and is used in professional platforms, and the DPS-310, a newer sensor with excellent performance across a wide temperature range, used in premium flight controllers. One important consideration: the barometer must be protected from rotor wash. The downwash from the propellers creates local pressure variations near the drone that can confuse the barometer. Most flight controller designs shelter the barometer under foam tape or in an enclosure that allows slow pressure equalization while blocking rapid pressure pulses from rotor wash. Beyond the IMU, GNSS, and barometer, the core sensing triad, there is a rich ecosystem of specialist sensors that transform basic drones into highly capable domain-specific platforms. Let me give you a two. Optical flow sensors are downward-facing cameras that track ground texture movement in the same way an optical computer mouse tracks desk surface movement. By measuring how fast the ground image is shifting in the sensor frame, the flight controller can infer the drone's velocity relative to the ground. This is enormously valuable indoors, where GPS is unavailable and the drone would otherwise have no velocity feedback. A drone with a good optical flow sensor can hover stably indoors without GPS, maintain position while flying through doorways, and perform smooth cinematic moves in GPS-denied environments. The DJI Spark and Mavic Mini series pioneered optical flow for consumer drones, enabling GPS-like hover stability indoors. LiDAR, light detection and ranging, sends laser pulses downward and measures the time of flight to calculate the precise distance to the ground. Unlike the barometer, which measures altitude above the takeoff point, LiDAR measures altitude above ground level, AGL, directly below the drone. This is critical for precision agriculture, where the drone must maintain a constant height above the crop canopy regardless of terrain undulation, and for obstacle avoidance systems that need precise distance measurements to nearby objects. Time-of-flight sensors, 2F, are similar in principle but use a broader light beam, trading angular resolution for simplicity and cost. 2F sensors are commonly used for proximity detection stopping the drone when it approaches a wall or ceiling. Pitot tubes are airspeed sensors used exclusively on fixed-wing drones. A pitot tube faces forward into the airflow and measures the dynamic pressure, the pressure increase caused by the aircraft's motion through the air. Combined with static pressure from the barometer, the indicated airspeed can be calculated. For rotary-wing drones, pitot tubes are unnecessary because ground speed from GPS and heading from the magnetometer together gives sufficient velocity information. But for a fixed-wing survey drone or long-range VTOL, airspeed is essential for stall prevention and efficient cruise. ADS-B, Automatic Dependent Surveillance Broadcast, is a technology borrowed from manned aviation. An ADS-B transmitter broadcasts the aircraft's GPS position, altitude, velocity, and identification code on 1090 MHz, where it can be received by air traffic control radar systems and by other aircraft equipped with ADS-B receivers. For large commercial drones operating in shared airspace, delivery drones, infrastructure inspection platforms, ADS-B capability is increasingly being required by aviation regulators to ensure visibility to manned aircraft. An ADS-B receiver on a drone allows it to detect nearby manned aircraft and take avoidance action. Thermal cameras detect infrared radiation, heat, rather than visible light. Every object above absolute zero emits thermal radiation, and the intensity of that radiation is related to the object's temperature. A thermal camera produces an image based on temperature differences rather than reflected light. In search and rescue operations, a person lost in a dark forest is invisible to a standard camera at night but glows brightly in a thermal image. In wildlife monitoring, animals hidden under vegetation are revealed by their body heat. In infrastructure inspection, thermal cameras detect electrical hotspots in solar panels, heat leaks in building insulation, and temperature anomalies in industrial piping. The DJI Zenmuse XT2 and H20T are professional thermal payloads for the Mattress series. Multispectral cameras capture light in specific narrow wavelength bands beyond what human eyes can see. In agriculture, the key application is NDVI, Normalized Difference Vegetation Index. Healthy chlorophyll in plant leaves absorbs red light and strongly reflects near-infrared light. Damaged or stressed plants absorb less red and reflect less near-infrared. By comparing the ratio of red to near-infrared reflectance, agronomists can map crop health across entire fields from drone imagery, identifying stressed zones before they become visible to the naked eye. The Parrot Sequoia, Mycosynth altum, and DJI Zenmuse P1 with multispectral capability are commonly used for precision agriculture mapping. We have covered an extraordinary amount of ground today. Let me bring it all together. We opened the drone and found 7 core subsystems. The frame, the skeleton, made predominantly from carbon fiber for its exceptional strength-to-weight ratio, available in size classes from 3-inch sinew hoops to 10-inch heavy lifters. The motors, BLDC outrunners, converting electrical energy to rotational force through electromagnetic interaction between stator windings and rotor magnets, specified by kV rating and stator dimensions. The ESCs, the translators that convert battery DC to 3-phase AC, communicate with the flight controller via D-Shot protocol, and increasingly integrate 4 motors onto a single 4 in one board. The battery LiPo chemistry, specified in cells, milliampères, and C rating, extraordinarily energy dense, but demanding strict safety discipline. The propellers, the final link, converting motor shaft rotation to aerodynamic thrust. And the radio system, the communication link between pilot and drone. We went deep on the flight controller, the brain that runs its control loop at up to 8000 Hz, processing sensor data and issuing motor commands faster than any human reflex. We explored the IMU in depth, the accelerometer that senses gravity and linear acceleration through proof mass capacitive sensing, the gyroscope that measures angular velocity around roll, pitch, and yaw axis using MEMS Coriolis sensing, and the magnetometer that detects Earth's magnetic field for heading estimation vulnerable to electromagnetic interference near power systems. We learned that sensor fusion, the Kalman filter combining gyroscope, accelerometer, magnetometer, and GPS, produces orientation and position estimates better than any individual sensor by exploiting each sensor's strengths and compensating for its weaknesses. We distinguished GPS from GNSS. GPS is one American constellation. GNSS is the family of all 6 operational constellations: GPS, GLONASS, Galileo, BeiDou, NavIC, and QZSS. We understood triliteration, atomic clocks, satellite geometry, ROP, and why 4 satellites are the minimum for a 3D position fix. We explored GNSS frequencies L1, L2, L5, and understood how dual-frequency receivers eliminate ionospheric delay to achieve dramatically better accuracy. We went through RTK and PPK positioning, centimeter accuracy, and the professional survey drone applications that depend on them. We introduced NavIC, India's sovereign navigation system, born from the strategic lesson of the Kargil conflict, now fully operational with 7 satellites, supported on modern smartphones, and critical to India's navigation independence. We surveyed the modern drone battlefield, FPV weapons in Ukraine, loitering munitions, electronic warfare, GPS jamming and spoofing, fiber optic countermeasures, swarm technology, and counter-drone systems. We went deep on GPS spoofing, how it works, why it is dangerous, and how multi-constellation receivers, cryptographic signal authentication, and non-GPS navigation methods defend against it. We covered the barometer, pressure-to-altitude conversion, BMP to AT and MS5611 chips, relative altitude measurement. And we took a tour of advanced sensors, optical flow for indoor position holding, LiDAR and 2F for precise altitude above ground, pitot tubes for fixed-wing airspeed, ADS-B for airspace awareness, thermal cameras for heat detection, and multispectral cameras for precision agriculture. What a chapter! This is the foundation. Everything that follows in this course builds on what you learned today. In Chapter 3, we are going to go somewhere extraordinary, deep inside the flight controller's brain. We will study how the PID control algorithm works intuitively, mathematically, and practically. We will look at Betaflight and RDU Pilot, the 2 dominant open-source flight controller firmware ecosystems, and understand what each is optimized for. We will explore the process of firmware flashing, radio binding, and sensor calibration. And we will cover regulations in depth, DGCA, digital sky, airspace zones, operator certification requirements, and how to legally fly in India and other jurisdictions. Chapter 3 is where theory meets practice, where understanding the hardware gives way to making the hardware do what you want. Before you go, here is your homework. Open the Gyroscope demo application on your smartphone. There are many free ones available. Search for Gyroscope app in your app store. Hold your phone flat and observe the numbers. Then tilt it slowly. Watch how the angular velocity readings change as you tilt, and how the orientation estimate updates as you stop moving. You're watching the exact same physics that your drone's IMU uses to fly. Second homework. Pick one component we discussed today: a frame, a motor, an escape, a battery, a sensor. Find its actual spec sheet or product page online. Read the technical specifications. Look up any terms you do not understand. Post what you found in the comments below, the specific component, the spec that surprised you most, and one question the spec sheet raised. Learning to read component specifications is a critical skill, and there's no better time to start than right now. I will see you in Chapter 3. Keep flying, keep learning.